Hey everyone, thanks for joining us for today's conversation, where we're going to focus on cosmology, one of our favorite topics to discuss in this series of conversations. And we're going to really try to walk through some of the essential features of the so-called standard model of cosmology, what they are and how we got to these ideas, and what observational evidence and what theoretical ideas have given us confidence that this is a step toward truth in the long human quest, really, that goes back thousands of years to have some understanding of how the universe began. And I'm so thrilled that our guest today is someone who has played a pivotal role in that story. It's Lyman Page, who is the James S. McDonald Distinguished University Professor of Physics at Princeton University, where his research focuses on measurements of the cosmic microwave background radiation. He is the recipient of numerous awards and honors, including the 2017 Breakthrough Prize in Fundamental Physics. And I believe he's joining us from his office in Princeton, although I can't swear to that. I have to double check. Lyman, how are you doing?
Hello, Brian. Nice to see you. Yes, from my office in at Princeton. Yeah.
Yeah, that really does look like a professorial office. I mean, I just have sort of this, clean and empty space, but you've got like the canonical look behind you there, which is wonderful.
Yeah. I need
Um,
them. That's the difference. I have to
yes,
keep referring to them. Right.
yes. So, as I mentioned, I want to take the audience through our latest thinking on cosmology. And that's a story that you've played a pivotal role in. You and your team and colleagues have played a pivotal role in.
Yeah. Thanks.
But
Yeah.
we also sometimes in these discussions like to step back a little bit and learn a bit more about the people that we're speaking to. So if it's all right with you, can we just have a little background on Lyman Page before we get into the cosmology? Will that work for you?
Oh, sure.
And
Let's
so
see.
where were you born and
San Francisco, and my dad was a doctor. My mom an artist. So he was a postdoc at the time, so we moved around a lot. So we went to San Francisco, to Palo Alto, to Virginia, to New Hampshire,
wow,
back to Palo Alto, and then to Maine. And
wow.
so
How
I ended up in
disruptive was that? How disruptive was that as a kid, or is it just something you took in stride because it's how things were?
exactly. Just took it in stride. I didn't know it would be disruptive, and it all worked out.
And we have a lot of conversation with both theorists, experimenters, observationalists. I come from the theory end of things
Right.
where it was all math for me as a kid. How about for you? Was math a vital, and were you like playing with, electronics kits and things like that?
Yeah. So I love math, but I was never a superstar in it. And I always liked building things as well. So it's sort of experimental. When I discovered about what experimental physics was, it just sort of naturally came together, and yeah, and it all worked. At least in doing experiments, we have to calculate a lot, which is good, and then trying to keep up with you guys on the theory side, right? We have to keep studying, and of course math helps out there.
Now, I read somewhere that that great big book on gravitation, Meisner, Thorne, and Wheeler had, I mean, it's had an impact on so many people. I mean, for me, absolutely, but you too as well, apparently.
Yeah, no, so my high school physics was nothing. It was multiple choice questions, and then I went to Bowdoin College, and I took a physics class, and it wasn't a very advanced one, but I didn't know what physics was before, and it just clicked. I just loved it, and so probably halfway through the semester or something, I went to the library and just started wandering down the aisle with physics books to see what this subject was about. I'd heard of course, everyone hears of Einstein and what was going on in particle physics at the time, but that book, the Mission Thornton Wheeler, just caught my eye, and I started
How could
looking
it
at it.
not, right? How could it not?
Exactly, the phone book, yeah,
Yeah.
and I just thought, wow, it completely, it just captivated me. So I say, okay, I want to be able to figure this out. I mean, this is of course way beyond me at the time. So then I took a differential geometry course so I could figure out one forms and two forms. And then I planned, the department was wonderful. And they let me plan a course around working through the book. So I took a 1-semester course with a professor and we started working through problems. And then it just, it grew. I just loved it.
And so you did take a background course. That's what I was wondering, because people who are familiar with that book will note that it's non-trivial. I mean, it's encyclopedic, but the mathematical sophistication, at least like especially in the so-called track 2. I don't know if you were doing track 1 or track 2.
I did track 1, but every now and then track 2.
Yeah.
Yeah.
It used to be that when I would give lectures when I was much younger and just sort of starting out, I would often give lectures with a track 1 and a track 2 to give me the leeway to go off a little bit more fully into the ideas and give the audience a break and say, hey, students or general public, choose your track, whichever one you work, much like a Mazda Thorne Wheeler. Oh, well, that's actually wonderful. And so you graduated in physics or?
Graduated in physics in 1978. And then I went to the Antarctic for a little over a year, working in a physics lab, a cosmic ray station.
But that's quite a decision, right, for a recent graduate, right?
Yeah, I can tell you. Yeah, so not to get too personal, so my girlfriend dumped me. I had taken the GREs because I said no, I wanted to go to graduate school, and I was I'd say a bit too confident, a bit too cavalier about them, and didn't do as well as I should have. So anyway, so the Antarctic was a perfect fit on all those fronts. So anyway, I went down to run this cosmic ray station and took a bunch of physics books with me.
How long were you down there?
15 months.
15 months.
So I wintered over, and then so I went down. So the McMurdo's on the coast, right? And it's this. It was a Navy base at the time, and then I was at the pole for a little while, and then back McMurdo, and then out to the pole. We put one of the first telescopes at the pole. This was with Martin Pomerantz of the Bartol Research Foundation was the guy who hired me, and we got, quite close. We worked together on this telescope, and then back to McMurdo, and then out.
And were there times during those 15 months where you were like, I cannot believe I'm down here, or was it all?
Yes, and at the same time, and it was much different. Their communications weren't like they were today. I'd talk to my folks maybe every month and a half or something like that. And it was a lot of time for thinking, sort of go into another zone, right? Your mind is in another place. And I just, I read a lot, Moby Dick, War and Peace, all those books you start maybe when you're in college and don't quite finish. And probably, at least to this day, the biggest impact thing I read was the Feynman lecture series.
Oh, you did?
Yeah. And it was, again, another time, so for those who don't know, it's an introductory book for a series of books for first-year students at Caltech. And it's funny, I read it, and I thought, even though I'd done a bunch of advanced work as an undergraduate, I just thought, oh, man, I just didn't understand physics the first time through. And it's just like it just opened me up to whole new ways of just thinking about nature and sort of reset and my mind and thinking about the world and thinking about physics. So that was great. And I had no.
That's an important point. If you don't mind, just we can emphasize that a bit, because I felt that way at so many points in my career too. I did the undergraduate courses. I did well on the exams.
Yeah.
But later on, I would read a description by one of the masters, and I'd be like, oh, that's what that thing was really all about.
Exactly. It keeps happening to me. Maybe not you, but it's just like, Oh yeah, you're just deeper and deeper and deeper, and it's nature's beautiful and subtle, and you can see these deeper connections. And anyway, Simon was
Yeah.
it was a real eye opener for me, and so
Wow. And so 15 months go by, and then
yeah,
you're ready to leave. And had you set up the next step?
I I thought I'd go to I'd apply to graduate school, and so then I talked with Martin Pomerantz, and he started sort of quizzing me about what I really wanted to do, and was it this, and and we sort of, I said, well, I'm not, there's some things I'd like to do before grad school. So I came back to the States and I bought a sailboat, an old wooden sailboat, and you could see through every plank. I mean, it was a mess. I paid way too much for it, but I was, young and confident. I'm sure I could fix it. And so I did. Anyway, I fixed it up over the next 9 months, and then
Was that by
sailed
yourself? By yourself fixing it up?
with friends, and I was in this boat. It was in a boatyard up in Maine, and the and it was a half working boat, lobster boatyard, and there were actually more than half, probably three quarters. And one friend would come up and help me, and and then one day we decided all the keel bolts were rotten. Those are what hold the keel on. All the keel bolts were rotten, and we said, okay, and this was he said, why don't we just cut it off? And it's like, my God, I just bought this new boat. We're gonna cut it off. And and the guys at the yard had been a little bit offish. They were like, who is this college kid who can pay too much for a boat? And anyway, so we jacked up the boat and we cut the keel off.
Wow.
And the guys in the yard just lit up. I mean, it was like they were like, oh, this is great. And so they came down with a case of Old Milwaukee and the bulldozer to help us haul out the keel, and they set me up with a guy to make new keel bolts who was up in Rockport, and then they really helped. I had some old wood that I could put in as a keelson, and then friends from school would come up and we'd hang out and paint and scrape and do carpentry and all that kind of stuff.
So how long did it take, start to finish?
That was probably 9-ish months or something.
Wow.
And then 8-9 months, and then sailed south.
And then
It was getting cold.
Then you went sailing?
I went to Florida, and then had, I'd spent all my money on the boat. So I was poor, so we just went south hustling jobs, and and then finally ended up in Florida. And and there I could trade getting a berth for the boat for bottom painting. So I worked in the boatyard bottom painting, and then slowly worked my way up in the ranks over the next almost year there. And then a boatyard's great because just people throw out stuff, and I just worked on the boat and fix it up and fix it up and fix it up, and then.
I mean, you doing physics reading while?
Yeah. No, I did. Actually, I was pretty disciplined. I read the whole time. I read Zemansky there. I remember I read Zemansky and Sears, I think it is, thermodynamics, and then I redid Marion. I always had my Mr. Thornton Wheeler, but I did physics the whole time.
But are you
not every night?
Are you just reading physics, or are you like setting yourself problems in the book?
Oh, definitely the problems. No,
Wow.
for me, I can't. You have to do the problems, right? So that was how I tried to.
Wow. I mean, that's so. You're basically putting yourself through your own physics education while sailing and fixing your boat and so on.
Yeah, that's probably too generous. I was just really trying to keep up. I didn't want to. I had loved it. I didn't want to lose it.
Yeah.
I think it was, and I just wanted to keep it in my mind and not lose that way of thinking.
And were you planning that this sailing was a temporary interlude, or were you just, just take it?
Yeah, it's funny. I was never quite sure. And so we went to by that time some college friends had joined me, and we sailed down to set off for the Virgin Islands, and the rudder fell off on the way. That was the one part I didn't fix. So we sailed into St. Thomas, or didn't sail. We, actually at the time we sailed, but without a rudder, steering by the sails. And so I had to get another job in St. Thomas. Then from St. Thomas, we were going to go to the South Pacific, and then and we were sailing, and so a friend, my roommate from college, had joined me by then. And we were getting the boat all ready, and it was going well. And then we were headed to Panama Canal, and then another part of the rudder failed. Actually, the mechanism to hold the rudder cracked. This boat was really old. It was a wooden boat from the 1930s, right? So it's getting old. So then that cracked, but we were dead set on getting to the canal. So then we jury rigged the sails, because we could sail pretty well, we could steer pretty well by the sails. And so it was in this configuration, it was a catch. So we did this wing and wing, sailing downwind to the canal. And then we just caught this bad wave one night, and the jib came up, and one of the hanks caught on the jib and ripped it in half. Mm. And it was that night, and it was I'd say a mild storm now, but it was that night. It was about 80 miles north of the Venezuelan Colombian border. It was that night. It's like, okay, time to go to grad school. It was just one of those thunderbolts. So it was like, yep, sailing's over. Time to go to grad school. And so we sailed into Jamaica and the Caymans and Belize and Yucatan, and I just and sailed into Boston. So
really?
Key West, sailed into Boston, and I started I think MIT was the first place I went. I walked in. And,
like what month? What month of the year? Was this like admission season, or was it just
No. So this was in must have been early June-ish sort of thing.
Right.
So not maybe a little later in the summer. So not then. And so I just wandered in, and I went to the admissions office, and there was no one there. And I was looking around, and this guy came up behind me, and he just said, "Well, what are you doing? Who are you?" And it was a guy named Herb Bridge, and he introduced himself. I gave him a brief, I'd done this, and now I want to go to grad school. And he said, "Do you have a resume?" And I didn't. And so he said, "Come around to my office, and my secretary will type one up for you, and we can distribute it." Because I wanted to get a job in a lab, show them I could do stuff.
Right.
And my secretary will distribute it. And I was sort of embarrassed, I was taken back. So I went and met some old friends and got a typewriter and typed up my own resume and went back to show I could at least do that. And then he gave me some names of people to talk with, and a good number of them said, "Why are you stopping sailing? What's wrong?" Anyway, and then one of the people I ended up talking with was Ray Weiss.
Yeah.
And he just said, "I can't pay you, but you can work in my lab, and you can do a project." And so
And just to remind our audience, Ray Weiss of Gravitational Wave fame, future Nobel laureate. And was he excited by your unusual background, or how did that play into it?
I think so. I mean, Ray is an extraordinary person, right? And I would say he had his tried and true MIT grad students. They're all super sharp and with it. And then he had a few outliers, and I was definitely one of the outliers, right? Who came in through different tracks or were just the chances, I would say. Anyway, just something, he was just open. He was also just really, really open. And I think he had enough of a different path, when he was going through grad school, that he was sort of open to the oddball case, and I was definitely an oddball case, so I think it was receptive. And then I didn't know how unusual it was. I mean, these things just don't happen these days. So
Yeah.
I just started, so I got a job as a carpenter out in Jamaica Plain. And
You mean
I
to
would,
pay for things?
yeah, so I could get an apartment and live and stuff like that. So I was a carpenter during the day. And then in the evening, I'd come in, and on weekends, I'd come in the lab. And then and then I studied for the GREs. I did well, or well enough, I should say. And then I applied to grad school. And there were just a few conversations with Ray that many stick in my mind, but a couple of them do. And I told him my plan, and he said, "Well, do you want me to write you a letter?" And I told him, "Well, I don't think you know me well enough. I can't believe this, in retrospect." And then he said, "Oh, you want me to influence it at that level?" So just completely, this pure idea of how well you have to know a person, all these sorts of, preconceived notions of how this works. And anyway, it was funny. And that was one. And the other was, I got my GRE scores back, and I did not look at them. I was just I was terrified. And terrified is too strong. I just didn't want to deal with this. And he said, "Well, how'd you do?" Because he knew I was taking them. I said, "Well, I haven't looked at them." You'll probably edit this out. He just looked at me and said, "You fucking ostrich." And he said, "Go home, get them, come back, and tell me how you did." And so anyway, it all worked out, and I got into grad school. I actually a few places, but of course with him. And then, and I started working, and Steve Meyer, who was my advisor, Ray was working on the microwave background at the time. And this was just when Ray was getting off into gravitational wave research. I mean, he started earlier, but he was really.
This is now mid 80s ish.
Yeah, it must have been. Yeah, exactly. It was 84ish, 85ish.
Yeah.
And then one day, early on, he just said, "Well," and again, it was one of these memories. We're sitting on the stairs of some building, and he had a pipe then. And he said, "What do you want to work on?" And this was between the microwave background with Steve, or on gravitational waves with his group. And he looked out. And he didn't give me a chance to reply. "Work with Meyer." That was it. And so that was just, it was glorious. It was,
now, in retrospect, either would have worked.
Totally.
Yeah.
Completely. Yeah. It's just, it's, well, it says
and so you graduated,
and volumes have been said about Ray, but it's just an incredible sense of, and both good projects.
So then you put a handful of years in for your dissertation. You graduated in 89, or is that?
Yeah.
Right?
Yep. So it was 5.5, 6 years.
Yeah.
Whatever,
right.
Yeah, 6 years maybe. So, and we were, I don't know how much of this you want to hear, but I'll just tell you anyway. So we were and building. So this was well before the anisotropy had been discovered, and we were. Ray, with Pat Downey, had developed these incredibly sensitive detectors, as sensitive as today's detectors, but it would just be 1s and 2s. And so there was my advisor, Steve Meyer, and then Ed Cheng was a postdoc with us. But Steve conceived of this experiment, a balloon experiment, sort of building on stuff Ray had done with Dirk Milner and Mark Halpern, to go after the anisotropy. And at the time, it was so we were building it, and it was a helium-3, helium-4 refrigerator that went up on a balloon with these super sensitive detectors. And
would this be a South Pole launch, or where would this?
No, this is before all that happened. This was out of Fort Sumner, New Mexico.
Oh.
So I think we were the first scientific balloon flight out of there.
Okay.
And these at these wavelengths, this is around a millimeter, which you go to the South Pole because of it's so dry. You go to, say, Chile because it's so dry, or you fly in a balloon because you get above the atmosphere.
Okay.
And we wanted to map a good fraction of the sky. So we built this system, and it was really sensitive. It was great, and we launched it. So this is my thesis flight, and we launched it from Fort Sumner, and in after 8 minutes, the guys from the balloon base leaned their head in our little room and said, "You're on the chute." So this thing I'd been working on for 5 years, right, was on the parachute. I was supposed to fly all night on the parachute, coming down, and because the balloon had burst.
Oh, really?
So it
Wow.
landed, and it landed upside down in a cornfield. So, and I went to find it. I mean, there were corn stalks in this in my experiment. It's like,
Yeah.
oh my, because it landed upside down, and because they didn't know where it was, they couldn't fire the squib to detach the chute, and so the wind had picked up, and it had just dragged the experiment upside down through this cornfield, and it was, oh no, it was brutal. But but with those 8 minutes, we set the most sensitive upper limit on the anisotropy. So
Wow.
that sort of gives you, at the time, yeah, it all worked. So anyway, we rebuilt it and flew it the next year. And then that flight was great. We got all night. So that was actually, it was October 1989. And that really worked. And all the detectors worked. And we did a bunch of analysis, and we knew we had a signal in our data, but we didn't know what it was. And we worked for, it was a couple of years, just trying to figure out what it was. We could tell. And we had some parts of the analysis. There was a bug in some software which confused us for a couple of years even. There's all these
Really?
little things that build up.
Wow.
And finally, I guess it was probably in around late 90s, early 91 or something like that, we started to, got the exact dates, but anyway, it started to make sense. We figured out, we found the bug, and we knew we had a signal, and I think, and we wrote a paper, and we listed the microwave background as one of the possible signals. It could have been atmosphere, could have been ozone clouds, could have been dust in the galaxy, but it could have been the microwave background. And
Did Kobe influence you at that time, or like how did that play into the thing?
Steve was part of Kobe, and Ray was the head of the science working group, but this was going on before they launched, so it was definitely in the air, that it was going on, and he'd heard about upper limits, and they couldn't tell me. So it was in the air, but then the real thing that happened was when Kobe came out. So we had this data. We made the maps. We published on them. We said we had a signal, and then we did the cross correlation. And the signal in our maps was the anisotropy, which was just, I mean, how thrilling can that? I mean, just, as a couple of years out of grad school, here is this this thing we'd measured, and it was great, and we gave it to the Kobe guys. Ned Wright looked at it, and John Mather looked at it, and Gary Hinshaw looked at it, and Chuck Bennett looked at it, and they said, yeah, and said, oh, we have this confirmation, a completely different wavelength, finer angular scale. Oh, it's just so exciting.
Amazing.
It's just, you can, those moments they stay with you forever, right? It was just really exciting.
Amazing. So maybe that is a good entry point to take a step back and talk about the cosmological ideas that you and Kobe and many other things that you've been involved with, WMAP, ACT, and so on, have really solidified our understanding. And sometimes people describe it, and I know you're one who also describes it this way as well, in terms of, they're just these six numbers that
Yeah,
we need to describe,
amazing.
our cosmological understanding. And we've had conversations about this before indirectly, but I thought it would be a good idea. Can we walk through those six numbers one by one just to make a clear
Sure,
description to the audience of what six parameters do you need to have in order to have a solid cosmological theory according to current understanding?
sure. I mean, you can trade. You can.
Yes.
There's some interdependencies, so you can pick your six.
Yes.
But let me start with the density of baryons in the universe, right? Just something like 5%, right, of the universe is the stuff of which we're made, and we're still figuring out where they all are, but we can see them just with clarity in the microwave background. And if you look at a graph of it, and it's hard to describe in words, maybe you've seen it, but if it, it's just the plot of the anisotropy. So if you don't mind, I'll just say a minute what that is. Here's the idea, right? We really, very simply, we just measure the sky. We just look up and we measure the sky, but in millimeter wavelengths or microwave wavelengths. So just millimeters to tens of millimeters. And we get this heat map. And then you can take that heat map and then you ask how much are big waves, big variations, and how much are small variations. And then to each one of those, you attach some number, so like a variance. And you say, okay, well, there's lots of variations with very, very long wavelengths, and there are fewer variations with short wavelengths, and you do those sorts of analyses. And then you plot those as a function of angular scale. And then you say, I'm going to look at some of the dominant fluctuations and compare them to some of the subdominant. And just that very simple ratio tells you the number of the density of baryons in the universe, the density of atoms in the universe. And so that's one.
Yep.
And what's cool is, right, we're seeing this picture from 380,000 years after the Big Bang. And that density works today as well, right?
Yeah.
13.8 billion years. Another one is the cold dark matter density. So, and it's a little harder to get at from the data, but so it just tells us the density of this dark matter, and we still don't know what it is. We're still looking, trying to identify it. We know what it's not. And certainly there are many, many, many more possibilities, and many people, including myself, are trying to figure that out. So that's but we know it has to be slow, not interact with light, and we know it had to be present at 380,000 years after the Big Bang. I think.
Yeah.
It's clear. Whatever it is was there. And then you can, the next one, you can switch in whether you want to have the Hubble parameter as a constant or say the dark energy as a constant. And let's just take the dark energy because it's more fun, right? So that's 25%, and 70% is this new thing in nature. I mean, it's been around, of course, since Einstein and de Sitter, but this new quantity that looks like the vacuum has an energy density associated with it. And you've written about all this, but you've written, right? I mean, it's telling us it doesn't come from any fundamental theory. It's telling us something deep and new about nature that we've got to fit in at some point. It just kind of like, who needs the modern version of who needs this?
Right.
It's there. And then, so those are the big descriptors. And then there are two parameters that tell us how the fluctuations, right? Something had to start the process of formation of all the structure in the universe, right? We look up, we see, of course, there's us at the small scale, the solar system, the galaxy, and then clusters of galaxies, and then huge filaments. And we see in the night sky this rich structure, and it had to start from somewhere. And the model is that there were these tiny, ultimately, trace back far enough, quantum fluctuations that were manifests and variations in the strength of gravity, and that cosmic structure grew by, and the contrast wasn't very big, but the cosmic structure grew by falling into these fluctuations. And so, and this is some primordial field of fluctuations, and it was posited to exist because we see the structure all around us, and it had to come from somewhere. But we can only characterize it, right? So it has to have, and the simplest characterization is it has some amplitude and it has some slope. How big are the fluctuations versus angular scale? And so those are the next two parameters, the amplitude of that and the slope of that, and the slope being magnitude versus angular scale, if you will.
By slope, you mean how the fluctuations depend on the scale?
On angular scale, yeah, right. I because I sail, right? Often think about it. If you're just out on the ocean, right, and you get swells, right? That's one angular scale. If you could translate that to the sky, that's one angular scale. And then there are little ripples and littler waves, and then eventually cat paws, right? And those correspond to the smallest angular scales. And then and the last parameter is the most squirrely. It's the most difficult to pin down. And that is that the universe, from when it started out to now, went through this, started out completely ionized, structure formed, and as our early structure started to form, it then lit up the skies again. So this is what the James Webb Space Telescope has seen. It's seen those early structures, and they lit up the sky, and that again, that ionized the universe again. So it went from ionized to neutral to ionized. And then in the history of that happening, we're still piecing together, and James Webb will be a key part of that. So it's a parameter, it's one parameter that characterizes that, when it's probably a rather complex process. But in terms of the microwave background, we can get away with just using one number to describe it. Yeah, so those are the six. And and so far, we don't need any extensions. That's amazing.
One way to judge a theoretical structure is, how much output do you get for how much input do you have to provide? Yeah. So how would you characterize the output that you can describe with these six numbers?
Absolutely phenomenal. I mean, I just, as you know well, right? The theory behind, there are many theories of theoretical possibilities, and there are some basic theories for how this would all work, laid down, decades before all this happened. But that you can describe this much of the universe with so few parameters is just absolutely phenomenal. And it's not just the microwave background. It's these same parameters work for no matter whether you count the different species of particles, Big Bang nucleosynthesis, whether you look for structure in the large scale structure in galaxies, this baryon acoustic oscillations, whether you just look at the expansion rate in various ways, there's some tension there, but the magnitude of, say, this Hubble tension is small compared to the big picture. Important, but small. But just that you can explain so much, and that if you use these six parameters to put into simulations of the cosmos, you get a cosmos that looks like ours. It's just astounding.
Yeah.
And I tell you, none of us, when we went down this path, were prepared. Maybe somebody was, but just we're amazed that this worked out. We were, even when we were conceiving of WMAP, it was like, oh no, the universe could be completely reionized here. Oh no, we don't. What's the geometry of the universe back then? We didn't quite know. I mean, there's just so many different possibilities, and that it could crystallize around these six numbers, and that these six numbers would last from the early 2000s till now is stunning, striking.
Yeah, totally.
So it's yeah, it's like, and I know, my colleagues and I, broadly writ, I mean, we feel like we just came of age scientifically in this magic time where the universe this part would just be revealed. I'm sure there'll be fantastic times, amazing times in the future, but for these decades, it's just like, my God, now we can explain so much. Not that we understand. No one knows what dark matter is. No one knows what dark energy is. Not that we understand all those things really deeply, but that we can describe so much so simply.
And so when you think about, and I'd like to get into the details of dark matter and dark energy in a few minutes, but maybe not dive into the minutia just yet. But do you think of this model as actually describing the truth of what happens out there? Or do you think of models more as just sort of this working framework that allows us to organize the data in a nice compact framework, but it's not really the truth of what's happening out there?
I would say heavily weighed. Towards the first. I mean, we have measured something new about nature, and from especially and someone who does experiments, it sinks deeply when you realize how fundamentally simple the measurements are. If everyone in the world could put on millimeter wave glasses and walk outside, if everyone in the galaxy could do that, assuming there are other entities, we would all see the same microwave sky. It's just, everyone sees the same stars. We're just looking at a longer wavelength. And the change was technology had advanced to the point where we could actually do the measurement. There starts with Penzias and Wilson, of course, and built up. But we just have this image of the whole sky, and we can all look at it, and we're not going to disagree on what we see. We're just, everyone is going to say, yep, that's what it looks like. And then it's, what is it? How do you describe? There are a million measurements or 10 million across the sky, however you want to frame it. And then you say, well, how are we going to quantify this? And then, it's, well, are the fluctuations Gaussian? Is it a Gaussian random field? And you can say, well, let's test that. Is that true? And then it turns out to be a Gaussian random field. Didn't have to be, right? But it turns out to be a Gaussian. Okay, well, now we can describe it by its variance. Well, how many numbers do we need to do that? Well, not very many. And then that you can relate those numbers to what's going on in galaxies, what's going on in the Earth, to fundamental physics. And there's these just links everywhere you go. It's not it's much more than a sort of a categorization, if you will, a tally. I mean, this is what is there. And if you had the right glasses, we would all agree. It's so simple, right? It's just so simple, and it's so measurable. I think that's the other thing. I think I would say there are many models that, and many aspects of cosmology that are on varying degrees of firm footing. They're beautiful. I love reading about them. Beautiful theories, but we know these things, these 6 parameters, just by measurement, and they're not hard measurements, and if you get to the precision we are now, they get harder and harder as time goes on. I should say they are hard, but they're not. The measurements on this, which is based, could be made by anybody with any moderately advanced scientific instrumentation. Right. And from there, it's just, you want to make a number for what you see, and so it's I think it's important to separate how deeply grounded an observation this is versus the more speculative and wonderful and thought-provoking aspects of cosmology.
Yeah, for sure. Now you mentioned WMAP, the Wilkinson Microwave Anisotropy Probe, which played an important part in nailing down these parameters. When did you start working on that? And was it just a rough idea that you then were able to pull together? Or, I mean, how did that come to be?
Yeah, so I came to Princeton I was at MIT. I came to Princeton to work with Dave Wilkinson, who had been my advisor's advisor and was one of, the grand figures of measurements of the microwave background. And I was, it used to be actually in this office right here. And I was walking by the door one day, and he just said, "Hey, Lyman, you want to work on a satellite proposal?" So I was an instructor at the time. So this was probably 1991. And I said, "Yeah, sure, this sounds good." And anyway, so a small group of us, so Dave and me, and Norm Jurasic, who's on the research scientist here, is still here and was, key on WMAP, and Ed Wallach, who was one of Dave's graduate students, who's also worked on WMAP. We just started working on designs, and then Dave and I wrote a proposal, and that was in '91. I remember that, and that was, in that proposal was the radiometer design. We ended up akin to it, not exactly the same. Norm independently came up with elements of it, but the layout of the radiometers we used, going to L2, Hempt amplifiers from NRIO, from Marian Pospizelski. The core I think most of the core elements you associate with WMAP was in that proposal. And then and we started shopping it around. So we went to, Dave was enormously well connected. And one of the first trips we went to Martin Marietta. Dave's vision was, well, let's just build it ourselves, and we'll put a tracking station over on the baseball field, and we'll get the data and we'll have a lot of fun. But anyway, so we went to Martin Marietta. Sandy Weinreb was working on amplifiers down there. We had a good meeting there. And then we went to JPL and had a good meeting there.
And this is before you have funding. So you're having these. Yeah.
No, and Dave had a grant from the NSF, which covered the group, and so that was, and then we got actually this. It turns out that proposal we wrote, that was funded. So then we had funding from NASA to work on elements of it. So we had little bits of money, but at that time it was NASA and the NSF, both absolutely essential for making any of this progress. Anyway, so we came back from JPL and we started working on, batting around designs when we could. And remember one of Dave's early slides was he called it PIE. So it was Princeton Isotropy Experiment. So this was before the Kobe announcement.
I see.
So this was, and it was pie in the sky was the joke.
Very nice. Very nice.
Anyway, so then what happened was we had a meeting, and we kept doing, I was working on ground experiment, other balloon experiments. We were it was an exciting field, right? And then we had a meeting at Goddard with that John Mather and Chuck Bennett and company had pulled together, and we just hit it off. It's just one of those, you get in a room with people and you can finish each other's conversations and worries, and it wasn't quite kumbaya, but it was good. Their ideas, right. and we could work with them. And I remember coming back from that meeting with Dave and Norm and I on the train. And, different things crystallize at different times for different people. And we were just all talking. And at least for me, like the whole thing just came together then. And came together for other people maybe earlier, maybe later, but I remember we were all so excited. It was the three of us were just talking, and like finally, someone's like, "Can you guys? I know you're excited." Somebody else in the train, just be quiet. It's like, oh no, you burst our bubble, right? We were just anyway. It was really, and that just, then we had a vision for how to do the measurement, and that was. That was it, and then we kept working together with.
How long did it take, would you say, from the initial vision to, launch?
Okay, so we probably put in a pre-proposal in 94. So the first stuff was from 91 to about 93 or 4. I've forgotten the exact dates. We were batting things around. And then from, it was around 94 probably with Goddard. And then it was 90, I remember the proposal very clear. The proposal that went in for the mid-X was 95. So that was a proposal. And we launched in 2001.
Right.
So it was just, it was fast. And it was also, we had done, Dave, of course, had been doing experiments for years. Norm is amazing. I've been working on experiments, and we knew exactly what we wanted to do. It wasn't, it wasn't a good thing for a graduate student to be part of. Wasn't a good experiment because it was no room for being wild and creative. It's just like boom, 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 boom. I mean, we knew the amplifiers we wanted to use. We knew it had to be improved. We knew the feeds we wanted to use. As Ed Wallach had worked out the first design. We knew the optical design we wanted to use, the radiometers, the electronics, because we'd used them all in the Saskatoon experiments. And we just, and then, the Goddard guys were fabulous, right? So we're putting together this spacecraft. And it was a time of, was it golden, faster, better, cheaper? So fortunately, the pendulum was just swinging, right? So we weren't the fastest, cheapest. We were a little bit afterwards, which was great. So we built in some redundancy, but we worked really hard, and everyone worked really hard. And then we launched it in June 2001.
And then when does data start coming in on that you can begin to analyze? Is that?
So it's about 100 days to L2, second Lagrange point.
Yeah.
But because we knew the instrument in the early pipeline, so it was, especially on the instrument, Norm and I and Gary Hinshaw and Greg Tucker we were at Goddard. So we saw stuff very soon. We could tell it was working.
Yeah.
And then it took a while to build up, start to build the picture. And I'd say, the picture improved every year. First, we had a couple of years of data, and then slowly polarization would come into view. It was a rollout as things got better and better. And I'd say the characteristic, and this we'd really planned on, was the data were super clean. I mean, I think it was roughly 95%. I've forgotten the exact number of the raw data go in the maps. I mean, it was just very.
I read somewhere it was actually 97%. Could that be possible?
Yeah, maybe. I was rounding. I was being conservative.
Yeah, right.
Yeah, no, it's just amazing.
I'm going to give you an extra 2 there.
Yeah, I'll take it. Yeah, it was just amazing, right? It just goes right into it was super clean, and we really understood the statistics of the detectors, and it's just super clean, and yeah.
And so with that data, you start to nail down aspects of those six numbers to a degree of precision that's, absolutely remarkable, right? We're these little beings 13.8 billion years after the
Yeah,
Big Bang on this rock, looking up, measuring, and nailing down to fantastic accuracy the
yeah,
numbers that you mentioned earlier in our conversation, right?
it was so cool. Yeah, they didn't all, they revealed themselves. I mean that index, right, took a while to come out,
Yeah.
but yeah, and it was, and although we often phrase it in terms of the six numbers, I think of equal importance is that it was like we could really test the Gaussianity, and we could do a ton of systematic checks, and we could compare one side of the sky to the other, and we could look in broad frequency ranges. And it was just this, it wasn't that looks about right. It was, no, this is the solution. It
Right.
wasn't, you could do chi-squared on the data and see that, no, this is for all this data. I mean, by the end, it was 9 years of data made into a map with a simple model, and that you could actually do a frequentist analysis and showed that that model fit down to the level of the error bars.
Yeah.
It just really, it hung together, and I think that was what was so important. There wasn't wiggle room.
Right.
Not that, we all expect there are additions to the model, but for these data, for the core foundation, that was the model. And that we were confident of at a level without, trying not to be hubristic or something, at a level that you just couldn't be confident of before.
Yeah,
Just
for sure.
because the data were so clean and there were so many systematic checks.
Now, you made reference a couple times to Gaussianity.
Yeah.
And I'm never happy when someone asks me to explain that to a general. It's a little hard. Do you want to give it a shot? Just
Oh, sure. Oh boy, yeah. Yeah. If you take a big class of students, and they take a big class, and they take a really hard test, right? So no one gets 100, but everyone knows something, and everyone's been studying hard, so no one gets a 0 and no one gets 100, and you just plot up the number of people that get each grade, right? It gets this nice bell curve, approximately bell curve distribution. So that's the Gaussian shape, and then and why it's so prevalent in nature is that just if you have a bunch of random things going on, like and you combine them, the distribution of that combination tends to follow that Gaussian shape. If you measured the I don't know, the frequency of small trees or something like that, and you went all over the world and you measured all of them, and you just plotted them up at different, okay, this one shakes at this frequency, this one shakes at this frequency, this one shakes, and you just plot a distribution, you tend to get a Gaussian. And that tends to happen whenever the thing you're looking at is made up of lots of subparts that are also random.
Yeah.
And so for the microwave background, which is what we're measuring, we don't shake trees, we don't take tests, right? What we do is we just look at the sky is divided up into 1 million pixels, and we take the temperature of each pixel, and we look at and we subtract the mean, subtract the average, and then we look at the distribution of those temperatures. And that follows this Gaussian shape.
Yeah.
And then, okay, great. It's a Gaussian, it's a number, it's a distribution, blah, blah, blah. What's so important about it? I think what's so fundamental about it is what a Gaussian is when things are Gaussian, it means that there are no funny, unexpected substructures. There are no deep conspiracies within the data. if you will. It's truly random. And it also, it says that the underlying, what the statistics of the large scale structure of the universe arose from some fundamentally random process. And
Right.
and so it's just, and if you say, you're an expert on inflation, right? That model of the early universe has to be random at some level. At some level, it breaks down at some very deep level, but the levels at which we can currently measure the fluctuations must be truly, truly random fluctuations in the sky.
Yeah.
And they look to be. We measure them to be. And so
it's worth noting theoretically that the simplest theoretical models are the ones that yield precisely this kind of distribution. We can add new terms to those models. If you guys would have found the substructure, there's a way that in principle that could be modeled mathematically, but so far it hasn't really been necessary to do that.
Yeah. And just another link there is, right, you associate this degree of randomness with thermodynamic equilibrium. That something has been able to come to some temperature. And so then you can see how that relates back to the early universe being in some thermodynamic equilibrium, changing, but in equilibrium, because the atomic
Very much
and
so.
subatomic processes are so fast that they can equilibrate it. So
So
I don't know if that helps, but it
really does help. I think it's really good for
concept,
people. No, I think it's really good for people to hear, someone who works with this stuff day in and day out, how you think about these qualities of the radiation and qualities of the data. But this is, look, an incredible success story that has only been pushed further still with the Planck satellite and other things that have been going on in the decades since. But if we could turn in sort of the second part of this conversation to some of the mysteries, right? I mean, this fantastic success story is not done, as you made mention.
I hope not.
Yeah, that's right. That's right. You made mention to dark matter, to dark energy. You sort of slipped in Hubble tension earlier in our conversation. I'd like to pull those all out a little bit right now, just to give people a sense of what we're still struggling with, and I don't know where it might go. So maybe start with dark matter. I mean, I wrote my very first paper as a graduate student in 1980 something, on a dark matter candidate. It's a sort of a natural thing for a graduate student. There's this unknown thing. Can you model it mathematically, and what kind of particle might it be? And I would say in the literature, there must be, I don't know, hundreds of candidates. I don't know, thousands. I don't know. That's probably overdoing it, that people put forward. Now, there are experimentalists who've been searching for a signature direct detection of the dark matter for a long time, and they haven't found anything. So the first question I have is, to what extent are you confident that dark matter is a real thing? And maybe as part of your answer, if it makes sense to you, to work in how different measurements of radically different varieties, like the CMB stuff that you were making reference to, as well as rotation curves and motions of galaxies, they all seem to give a consistent dark matter value. And that seems pretty convincing. Be quite a coincidence if it's wrong, right? I mean,
I would say, I mean, okay, so what's, going back to I guess, the big mysteries. So what is this dark matter, and why do we think it's there? Let me just say from the, and what could it be? You touched on all these things, but if you don't mind, I'll just add a little bit to them, right? Just say from the microwave background side, right? You have to have dark matter as one of those 6 parameters to describe what we see, to describe those million data points in the sky. And the dark matter has to have the characteristics that it doesn't interact with light to any appreciable degree, and that it's not relativistic, that it's relatively slow moving, right? It's not like a neutrino or something. It's not like light, or it's not of similar nature. It's relatively slow moving, so it can make clumps gravitationally, because it's the dark matter that if you will, digs the potential well, right? That the baryons and everything else fall into to make the galaxies. In that, as you said, it's the same density of dark matter that you get from the microwave background as you get from looking at local groups and galaxies and rotation curves. That all hangs together. And there's even I think to me another cool piece, and that it shows you that it's whatever it is distributed throughout the universe and clumpy. And that with the microwave background, right? We think of it as a sphere around us. Many times it's because the microwave background photons were set free in a relatively short amount of time, very early on. So when we look up at the sky with our magic millimeter wave glasses and see it, it's coming at us from the edge of the observable universe, and it's streaming to us, and it's been streaming to us for 13.8 billion years by all the matter in the universe, by all these galaxies and clusters of galaxies and things like that. And what that does is it slightly alters the direction. So when we look up at the sky with our glasses, we actually see a slightly perturbed signal, not by much, by very little. And it's be like looking at someone through shower glass, maybe. They're just all those galaxies and clusters, they act as little lenses to deflect the light just a little bit on its way to us, a tiny amount. Just something like a tenth the size of the full moon. And then, but what we can do now, the maps of the microwave background have gotten so precise that we can measure that to 2% accuracy. And so we can then, what that allows us to do is, if you will, look at the volume of the universe. So no longer the shell on which those 6 parameters are based, but we can now look at all the stuff inside too, and see if the model that gives us the shell gives us the inside, right? That gives us that the same thing that goes on the shell goes on the interior. And to the limit of measurement, which is 2% accuracy, it does. It's stunning, right? So we know this dark matter is distributed throughout the universe, that it was there early on, that it is here now. It doesn't. So to my mind, and we know it's slow. So if you could gather enough of it, you could put it on a scale and weigh it. But it doesn't mean it's of a sort that we'll be able to measure in a decade or even 50 years. Nature's so rich, right? It might be something that you can only measure cosmologically. I hope not. I should say the other, outside of the microwave background, the other thing I'm working on is an experiment to search for axions, which is one possible version of it, one type of particle.
I mean, you're working on an Axion detector now.
Yeah. It's my last CMB experiment is in Chile. It's taking data with part of the Simons Observatory. But I've really, with a colleague here, Satarshi Chowdhury, we're building an Axion experiment. We just sent out the cryostat for a quote. Just sent out the dilution refrigerator for a quote. We've been working on it for a couple of years. So we think those are particularly exciting.
Yeah.
So that's just one kind. Or they might be they could be black holes everywhere.
Yeah.
But just I think the window on those is getting tighter and tighter. They have to be in a specific mass range, which I've forgotten. But that's another possibility. There are just so many other possible things that it could be. So and of course, it doesn't have to be one thing. Maybe there's a whole rich zoo of new particles. And it's
the simple universe that we started talking about, maybe it's simple at a certain level of analysis, and then you go deeper and all of a sudden Pandora's box opens and there's all sorts of
Yeah,
stuff contributing to what we've long since called dark matter. Maybe it's all sorts of things.
totally.
But can you imagine any observation changing your mind about the existence of dark matter? Or is that just really, it just can't imagine it?
I would, well, if it's a good measurement and done well, you've got to take it seriously. But I would be surprised. I mean, it's someone takes the time to take good data, and the first thing you have to do is confirm it. And if it holds up, take it more seriously.
But what would it be? I mean, can you imagine what that? No. Okay.
What that experiment would be?
Yeah.
I think if there were one,
You'd be doing
I'd
it.
be trying to do it. You don't make progress in the field by confirming what everyone knows, right? You make progress by, looking for something new or probing it or pushing it really hard or measuring something better than anyone's measured it before, right? That's the only way. And that's on on our standard model of cosmology, I'd say that's it's one of the triumphs and one of the challenges, right? The triumph is it does so incredibly well that it's a bit alarming, and I think you want to take any deviation seriously and look into it as hard as you can and look for deviations. And we know they have to be there at some level. The models can't, it's not going to hold all the way down. Right?
Yeah.
And the dark sector, whole dark sector is, I would put the cosmological constant, that's great to pursue. I'd say it wouldn't surprise me if that were something fundamental we still don't see right. But in terms of dark matter, it's got to be there in some form, at some level, at some degree of complexity. And
Right.
we just have to keep looking think about it in different ways. So if it were measurement, I'd probably try to do it. And if someone came up with another measurement that said this shows it's not there, I'd wait a little while, wait until someone confirmed it, and then look into it more carefully. Yeah.
Right. And so your level of confidence in, well, I mean, dark energy is a funny term, as we all know. It's just a catch-all phrase for something that acts as if it were Einstein's cosmological constant during a particular era of time. It can exert an outward push. But your confidence that even effective description, even if fundamentally it's maybe something else, your confidence in that is as strong, you would say, as in dark matter, or not quite as strong?
Oh, for lambda, for the
Dark
cosmological
energy,
constant?
yeah.
Yeah, I mean, it would be, great to be able to tell if it were some kind of scalar field, but for me, that's going to take a long time.
Right.
So I'm from where we are now and what's, I'd say, accessible by measurement, and I'm be surprised if that were the first place we found something new. And I know there are more of their recent data coming out that said maybe the sector is much more complex, but I'd say let's wait. Let's just wait. And it's so. And again, right? I mean, beautiful measurement, beautiful experiments, and there are, some conflicting measurements, and let's just see what happens.
Well, I'd love to turn to some, conflicting measurements in a second. Hubble tension is a natural place to go, but before we go there, much as with dark matter, just to emphasize to the audience, dark energy is now also distinct measurements yield, again, a confluence of interpretations in terms of dark energy. So you've got the supernova early on, but now you've got CMB. I mean, so how would you describe the lines of convergence for the existence of something like dark energy?
It didn't have to be that way.
Yeah.
It's astounding, right? That it is as close as it is, and I think it just gives us faith in that we're on that's nature, and
Right.
you can look at nature in multiple different ways, and you get the same answer,
Right.
and not just, I mean, you mentioned the CMB and the supernovae, and also these large galaxy surveys,
Yes, for sure.
DES, DESI, right? And it's from those that, right, there's now like, oh, maybe it isn't quite as simple as a cosmological constant. And that would be just going back to, that would be wonderful. I hope that's true.
I
That
mean,
would be
the
neat.
DAISY results that maybe it's a decaying dark energy over
Yeah,
time
something
or
like
something.
that. I think that would be great. And I'd love it. And then if that withstands the test of time, a few more measurements, and there are instruments out there that can do it, then let's take it more and more seriously. For me, it's not quite at that level yet.
Yeah, right.
And so versus, sort of difference, a departure from the standard model in that sector, which would be cool. Deep,
Yeah,
but I mean, it's so fundamental. It would give a new insight into fundamental physics, but
right.
so hugely important, and I hope it's true. I'm just not,
Yeah, right. I mean,
just
it
not
just
there.
opens up a whole nother
Yeah.
area of study if it is. So maybe you can turn to the Hubble tension as again
Uh-huh.
one of those moments that might qualify for your, find the deviations and take them really seriously as a way to
Right.
make progress. So we've had conversations about this before, but I never like to assume that people remember the details of previous conversations because half the time I don't.
Mhm.
So maybe you can just give us a sense of where this Hubble tension comes from.
Sure. So, uh, in one way of measuring the expansion rate of the universe, or the Hubble constant, you get a number, and I'll just give the number. So we have you get around 73 or 74 kilometers per second per megaparsec. And so this is done with supernova, and Adam Rees has led a large group to do this, and it's been and so he gets this value, and there's a lot of credibility going in because it was through the supernova that we first got a sense for the accelerating universe. So you can
Yeah.
take this very seriously. But the and that measure that the data and the measurements have undergone a lot of scrutiny, and a lot of people have tried to knock it down, and it has survived. So take that seriously as well, and I certainly do. So something's going on there. Is it cosmological? I don't know. But and is it, I talk with Adam Rees about this not infrequently, and I'm a little skeptical of the error bars, but that's because I come from it from such a different side. So that's that side. But I would say it's definitely different than what you get from the more cosmological analyses.
Yeah.
So
So
then you
what do you
go to
get from yeah. Maybe you can
from the
describe the
microwave
cosmological
background is
side.
on the
Yeah.
other side.
Yeah.
And and there it is, you can take those 6 parameters we talked about, and you can rephrase, you can substitute in one for the other because there's an interdependency. So you can talk about the Hubble constant and put it in there. And there you get 67, 68, something like that. And so definitely different, but it's a very, very different measurement. One is cosmological in that it comes from measurements across the sky, multiple frequencies. It comes from and on the microwave background side, you can throw out some aspects of the data and combine with galaxy surveys, again, over wide swaths of sky,
Yeah.
and get the same thing. Or you can even throw out some other aspects and focus on Big Bang nucleosynthesis and bring that in to nail down some of the parameters. And it all settles in around 67, 68, 69, somewhere right in there. So when you look at these large surveys, you always get this lower value, this slower expansion rate. And so that's the tension. And then you go and you say, okay, let's take the tension at face value, and you say, okay, if these measurements from, I should say, relatively nearby, because they're supernova, they're not these, they're not, say, going back to the microwave background, and not relatively nearby isn't quite the right word because they go out astoundingly far in redshift by any measurements, but compared to the microwave background, not. But let's take it seriously. So if this is true, how can it happen? Is there some new form of dark energy that an add-on, so you can then test for that? Or, so you can come up with various models to explain the difference. And now, so then it goes back, in say the cosmology court, the microwave background large galaxy surveys court, say, do any of these can we test these models to probe the Hubble tension any more deeply? And that's starting to happen. And so it's unambiguous that, because no matter how you measure the Hubble constant with the microwave background, you get the same value with surprising accuracy. And now these secondary, now you take the supernova measurements seriously, you take the predictions, you then compare the predictions to what you see in the microwave background, and that's going on right now.
Yeah.
And that'll take a while to get really precise, but it's testable. That's a big thing. And then, of course, there are other measurements. Wendy Friedman and colleagues have have another method, which is in its early days. I'd say it hasn't been as scrutinized as the supernova measurements, but those will take time. And then my favorite is more neutron star black hole mergers, from LIGO and LIGO and its subsequent generations. That will be fantastic, right? Because you can make a very precise. We don't have enough now, but once you get enough, you can make
amazing. Yeah,
that seems to me particularly clean, and you're not relying on galaxies or properties or stars or anything like that.
Right.
Just relying on simple objects and geometry and general relativity, right?
Sure,
So you can know all the elements at sort of not quite first principles, but
yeah. Now, you made brief reference to Wendy Friedman's measurements. Yeah. We did a conversation with her, I don't know, maybe it was a year ago now, could be that long, where she seemed to be suggesting that her data at that time, the value of the Hubble constant was sort of moving closer to the cosmological one, and they were overlapping enough that she imagined that the tension was becoming less tense and going away, perhaps. And then we had a conversation with Alex Filipenko, and Alex was like, well, I don't know. When you look at this full set of, 42 supernovae, not just the 10 or so that Wendy was focused on, the values of the Hubble parameters seem to pretty clearly not overlap, and there's a real tension. Do you have a sense of where that is going?
Oh, when I look at the most recent of the tip of the red giant branch measurements, which is, these are all really all sides are really difficult measurements. To me, it looks like it just, with taking the error bars face value, it straddles the microwave background measurements and the supernova measurements, and the error bars are large enough that it just says, let's get more data, look at it, refine the measurement, get more cross checks. It's promising. I mean, it won't be long before the error bars are down by a factor of 2. It's just this combination of figuring out the galaxies, figuring out the right, ever more deeper understanding of the red giant branch, and then how to do the subtle data analysis. So I'm bullish on the whole program. It's great, and it's just something that has to be done, and I think it's fun to speculate, but putting on the 10 or 20-year hat, right? It's really great science, because we can make better and better measurements, and people can cross-check them, and that will be done, and we'll find out if there's something new in nature.
Yeah. Yeah.
rather than some subtle astrophysical thing we haven't thought of or something like that.
So do you
You can see
work?
I'm definitely on the CMB side of the.
Yeah, sure, sure, of course. That makes perfect sense. But looking in your 10 or 20-year time frame that you make reference to,
Yeah.
do you at all worry that things have worked out too well so far and that maybe this science reaches the end of what it can productively do with the level of technology and equipment that we have, and we'll just sort of have a really good story and there won't be enough motivation to keep on building and studying and pushing things further on?
Not much. I mean, it'll get harder to measure the new things, but we know there have to be neutrinos out there, and they're not. Their mass is not part of our current model, but they
Yep.
have to be there. And so this is. This is deep and fundamental, right? We have to, and we can do it. So it's just I had hoped it would be done. We'd have a good handle on the neutrinos right now, and maybe they aren't going. Maybe the measurements will turn out to be not what we expect, but we can probe those through cosmology in a way that you can't on the Earth with the terrestrial labs, in a
Right.
absolutely complementary way. It's not one or the other; it's a complementary way. But that's so. So that's just one example of something deep and fundamental to our understanding of nature that we'll get at through better measurements of the microwave background. And galaxy surveys, right? There are multiple ways you can get at this and multiple signatures of neutrinos. So that's
Yeah.
just one. Another example is, why are there three families of particles, right? Is that really true? Is there something masking as a half? Why? We can measure that with a microwave background. So
Yeah.
that's a hard measurement, and it takes time. And so it's sort of I think of it somewhat akin. We're not at the stage where, say, particle accelerators are. There's still maybe we're particle accelerators in the 70s or something like that,
Yeah.
right? There's a rich landscape. At some level, it's got to be non-Gaussian. The distribution has to be non-Gaussian, and that would be another absolutely
Yeah.
stunning measurement. And it's also, I'm not sure. The sky, it can be Gaussian in one way, and it can be non-Gaussian in a gazillion ways. And technical term, right? Whatever. And it's
Right. Anytime a correlation, unexpected correlation.
right.
Yeah.
Let's get do we have the right statistics? I know my colleague thinks that this is Jim Peebles, right? It's like, no, there are correlations in galaxies that don't come from purely random processes, types of galaxies, and maybe that's manifest in the microwave background. We just don't have the right statistic yet.
Mm.
And so there are a lot of things like that, but then for the CMB, which is it's so it's a lab for fundamental physics, and at the same time, there are so many more astrophysical things to do, right? It's just millimeter wave transients, right? It's a whole new region of the spectrum where the instruments have gotten good enough to look at the sky in whole new ways.
Sure.
To just, clusters of galaxies and imaging. You've gotten to the point where we're starting to image filaments between clusters of galaxies, right? And then you measure more carefully and you get the lensing of the filaments. So you're measuring the mass, and then you start to map out the universe in yet new ways. So there's a ton, and again, primordial gravitational waves, BMOS, and of course, so they're just a myriad of exciting
Yeah.
and things to do that are new ways of looking at the sky, and so not as simple as 6 parameters, but maybe a 7th parameter or an 8th parameter, but then more just great astronomy, great physics.
Yeah.
So
Yeah.
I'm pretty bullish on the future.
So if you have a little more time, there were three other things I wanted to just quickly touch
Uh-huh.
base on, and you actually made reference to one of them a moment ago, which is when we try to come up with theoretical models describing the cosmology that the six parameters is encapsulating, for a long time it was inflation. That was kind of the lone theory that was pretty
Yeah.
much the go-to framework for describing everything. And then, this interesting sociological phenomenon with your colleague, Paul
Right.
Steiner, who is one of the developers of the inflationary theory. We've had conversations with him in these series as well, has pretty much changed his perspective and has been in this cyclic approach to cosmology.
Right.
One of the main differences in them is their disposition regarding primordial gravitational waves. Uh, so what do you think maybe you can describe the difference in these two approaches and what they're looking for or not when it comes to primordial gravitational waves and the likelihood that we could settle this in the next 5, 10, 15 years?
Sure. I just thought I could just some background. So I was a grad student at MIT, and I took field theory of the early universe from Guth.
Guth, right.
So I was, and that set in my mind. And my colleague Paul is just down the hall, right? And so he's been working on dislodging it. But I'm slowly understanding what he's talking about more. But many of my mental pictures are still inflation related. I think because of super horizon fluctuations exist, and I know they come out as cyclic models, Okay, but back to testing them. So I should say the experiment, one of the experiments I'm working on now is an experiment to search for these primordial gravitational waves, which would, if they're present at sufficient amplitude, would manifest themselves in the polarization of the microwave background at relatively large angular scales. 10, 20 full moons across. That's the angular scale of fluctuation. The bicep Keck measurements, I think, are the best now, and they're putting great constraints on it. But
Bicep had its own little hiccup along
yeah,
these lines, but I guess
yeah, they had that hiccup. Yeah, and so and like any, and I'd say this is true certainly in this field. I'd say for any measurement in physics that's pushing the boundaries, you need to do it a couple of ways to believe it. There are assumptions that everyone makes. Having two different measurements, preferably competing, not nastily, but trying to prove each other wrong is and again, not nasty, just trying to prove each other wrong, and is the way to make progress, right? You want to be, it keeps you sharp, it keeps you critical, it even costs less in the end. But so anyway, so the Simons Foundation funded us for one of these experiments that we're working on now that is should be very competitive with the bicep measurement, so we can have an independent assessment of where they are.
Yeah.
So that said, so where are so where are we? So here's this maybe it is the seventh cosmological parameter, would be the omega gravitational waves. Right? So if inflation is, the simple models of inflation are correct, all the models I learned, there should be an amplitude of the polarization of B modes, or the tensor to scalar ratio is the more formal term, that we should have already seen. And we passed that limit a long time ago. So, but inflation is, and far more than I do on this, it's a flexible theory, so it can predict.
Which is part of Paul's criticism,
Totally, yeah.
Yeah.
Right. It can accommodate any level of fluctuations, depending on who you talk to and when you talk with them. And in the cyclic model, so this is we'll just call it I'll just use the tensor to scalar ratio, right? It's got a certain value. That value is being pushed down now. So the cyclic model says these shouldn't exist at measurable levels. These fluctuations, these primordial gravitational waves, they shouldn't be there at measurable levels. And so in some ways, this is, it's very clean. If we can measure these primordial gravitational waves, these tensor fluctuations, we can say that these cyclic models just don't work. And so it would say the universe isn't cyclic. However, if we can only push them down to some limit, and that limit is something like a factor of 10 below where we are now, and maybe you work much harder, you get below that, but you said 10 years, so I'll take that. A factor of, say, 10 below where they are now. Then all the simple models for inflation will be not working.
Yeah.
And these cyclic models will be, will still be viable. And so it's interesting both ways.
But you do agree that there's at least a chance that we'll be in this curious situation where somewhat less simple, more baroque inflationary models will be compatible with the absence of primordial gravitate, and send them are in sort of this funny place. But I gather after a while, I presume it would settle out because people who come at it without any preconceived notion or desire will just look at the simplest theory, presumably at some point.
Yeah, I'll just say, oh, that's the way it is. I mean, I ran into there was actually a retirement dinner here, and David for Kurt Callan and David Gross was here, and I'm just reminded. I mean, I think when those guys first came on asymptotic freedom, I don't know if it looked beautiful. I mean, you'd know much better than I would, right?
Yeah.
I thought that looks really complicated. Why is nature like that, right? And then slowly you get used to it, and then all of a sudden, my God, that's the way it is, right? And maybe inflation, I think, maybe along the lines of what you were saying, it will end up like that. Like, oh yeah, of course, everything has two fields that go like, two fundamental fields that work off each other.
It is a funny thing how what seems complex to one generation can just be shrug your shoulders and accept it in the next generation. So these aesthetic judgments, which ultimately for a while this may come down to, we just may be uncertain which cosmological theory to go with. But look, if you find the primordial gravitational waves, I mean, that would be the cleaner.
Yeah. And you have to look. I mean, this is so, it's just so deeply ingrained in cosmology. And again, another, a cross-section, intersection of our view of fundamental fields and actually what the universe is doing. It's going back to that ultimate laboratory, the Big Bang or the Big Crunch or whatever.
Yeah, totally. Yeah. So the other thing that I wanted to quickly touch on is people have heard that, James Webb Space Telescope, revolutionary new data that is showing the Big Bang is wrong or blah, blah. I mean, well, I'll leave it to you. Where do you come down on these guys? I mean, to me, it's just complex astrophysics that we don't fully understand.
Totally.
Yeah. Okay.
No, I'd say, let me just say the first thing. James Webb Space Telescope is an absolute marvel. I mean, I would say it is I'll use a superlative here. I'm thinking through. Maybe the most sophisticated instrument humankind has yet produced. I mean, the particle accelerators are big and massive, but this is at L2. This is 1 million miles away, incredibly sensitive, and really hard. And it's like whatever tennis courts. I forgot how many tennis courts. I mean, absolutely amazing instruments, and giving us new pictures of the universe. And I know there are all kinds of ups and downs with funding in Congress and all that, but this is something humanity doesn't do every day, right? In fact, it will be I don't know how long before it can match it. It's just absolutely amazing what NASA did with it. It's beautiful. Okay. Yes, early results came out. Oh, the cosmological model is wrong, but it's challenged. These shouldn't be here this big, this soon, this one, that. But I never phased me because, I mean, we don't know how galaxies around us are formed. I mean, it's a hard problem, right? I mean, there's so much astrophysics, and it's beautiful physics. And I think even now, if you look in some of the more recent papers, no, it actually doesn't deviate so much from those early releases. But it's almost always, something comes out and it's exciting, and you have a first analysis, and you have your notions for what you should see, and you're excited, and the data are probably all correct. Just the interpretation is needs to be updated, and you learn more. And I mean, it's the story repeats, right? You look at something and you just dig in, and then a grander picture is slowly revealed. So I think they're in that revealing that bigger picture right now, which is also just stunning. I mean, I look at those plots of black holes versus redshift, the number. I mean, it's just so cool.
Yeah, no, it's wonderful.
So anyway, so a beautiful instrument, beautiful results, but I'd say not a challenge to the standard model.
Yeah.
Not that I wouldn't have loved to have one.
We would love it.
It'd be great.
No, I agree. I think it's important for people to realize we love it when the models break. That's a real opportunity. But to say that they've broken prematurely based upon observations that require such complex physics that we haven't yet fully grasped is just really jumping the gun.
Fully agree.
Final question on the science front here, though. You made reference to you're now doing your last CMB experiment. What makes you sure it's the last?
Oh, it's a great field. So I have lots of colleagues who are taking it to greater heights. But I've just, I got the bug when I was a grad student, and a whole bunch of times I just, I was thinking, I guess I can't do the same science my whole life. But the thing with the CMB, it's just been, reassess not infrequently, but it's just like, oh man, we can figure this out. Oh, we've got to go do that. Oh, we can figure this out too. Oh, we've got to try. It's just every step what we could learn just got grander and grander and more interesting and deep, and I just couldn't not do it. Basically. Anyway, so I'm working on this experiment with a large group in the Science Observatory and a small group here, and it's searching for these primordial gravitational waves. It's fun. I love it. But I'm also a few years ago finally, and now it's a big field, and there are a lot of people doing these measurements, and so I wanted to do something different. So I just started working on that. It's not got it, so it's got a great future, and it's just great science. But and it's also it's this for me also. It's this probably too long-winded an answer for your question, but it's the cycle of, you build an experiment, an instrument, and you take data, and you analyze it, and that's sort of that's sort of a 6 to 10 year process, but you do it all. And now, so the instrument's great. We'll take data. The analysis will be done certainly by us. We'll do but a lot of people will do the analysis, and it's just a bigger field now, appropriately so.
Yeah.
It's just a different flavor. It's just a different flavor, and before I got too far along, I wanted to try something completely new. And the Axions are just so, there's the strong CP problem. It's been hanging out there, and it's another case where the technology has arrived, so you can really start to make inroads. And for the measurement process is this nice confluence of particle physics, of trying to evade the standard quantum limit to probe deeper and deeper into the coupling constant, this relation to dark matter. And it's, you know, there are a lot of new experimental techniques growing. It's a lot of fun, and I think that, you know, it could really lead to something.
Yeah.
Maybe not in my next few years, but after
Well, hey,
that, it's exciting.
if you detect axions,
Yeah.
you
Well, we'll
can
be
buy
in touch.
your ticket to Stockholm on that one, right? So that's that would be an amazing thing. Well, look, it's been a great conversation, Lyman, just to
Yeah.
hear about your incredibly interesting pathway toward being a
Yeah.
physicist, and then all the wonderful work that you and your colleagues
Yeah.
have done and are continuing to do. So I am pulling for you to find those B modes, those
Oh,
primordial gravitational waves. I'm pulling for you to find the axion.
yes. Good. Thank
And
you.
you know, best of luck going forward on these exciting projects. So thanks for
Yeah.
joining us.
Oh, thank you, Brian. It's a pleasure, and thank you for the festival. As you know, paths have crossed through it many times, and it's
Yes.
a wonderful thing you and your colleagues are doing. So,
Thank you so much.
thanks.